My name's Andrew Blakey. I'm a software developer with Locus Robotics. Today I want to talk about how we can leverage the tools of the geomatics trade for spatial analysis of real-time and historical robot data. So mobile robotics environments produce and consume a large amount of spatial data. When we want to analyze these data, we're interested in things like understanding the real-time and historical state of an environment. We want to explore what spatial relationships exist among data themes. We want to perform geoprocessing tasks to derive higher order data products. And we want to communicate those discoveries with other people. Doing this with existing tools, which is usually RViz, can be a very uncomfortable experience. Exploring data can be an expensive task, especially if you don't have a strong sense of what form your results will take. You need to work within the limitations of how data can actually be visualized in RViz, and you often have to author custom nodes if you want to generate data products, or even additional topics if you want to do things like label and other symbologies. Sharing your findings often involves taking screen captures and cleaning them up in post. And this creation of additional nodes and topics can mean that you're mixing your visualization and analysis environment with your production environment. And this makes deeper analysis of production systems a much less palatable exercise. We also end up spending a lot of time building our own tools. So this brings us to the core of why I wanted to give this talk. There are some very powerful tools that we can use to make better use of in robotics for spatial data analysis. GIS, or Geographical Information Systems, is a geomatics paradigm that, put very simply, lets us use computers to explore spatial data. So a GIS environment makes it easy to access data from a disparate number of sources and formats, visualize these data in an intuitive way, explore the spatio-temporal relationships between different themes, produce higher order data sets by building geoprocessing pipelines, and then publish meaningful results in a variety of media such as web applications, print format, or even new data sets. One implementation of a GIS environment is Qgis. Qgis is a Qt application that runs comfortably in Ubuntu with both a C++ and a Python API. And I think the use of these technologies likely makes Qgis a natural fit for the ROS community. So how do we merge a GIS environment with a ROS environment? To do this, I authored QGIS ROS, which is a QGIS plugin for accessing both live and bagged ROS topic data. It supports vector, raster, and non-spatial data, all of which can be sampled or subscribed to, depending on your needs. It supports custom message types, allowing you to involve your own data schemes with relative ease, and it's available today, so I encourage everyone to try it out and break it in unbelievable ways and share your support issues. So here's what it kind of looks like to have QGIS with the QGIS ROS plugin running. Here I've got a list of all the topics available in the current master. I've subscribed to some of these layers, which then appear in the top left, the table of contents. And then I've got an attribute table open for my robot layer. As new data is published to these topics, the visualization, the tables, and all the dynamically calculated fields that you might have created are automatically updated on a regular interval. You can also configure processing tasks to be automatically run on new data that comes in. So what exactly can we do with this? I've created a number of examples, none of which required any code, all of which took just a few minutes to execute. So this is a very quick ability to do analysis. Processing pipelines are a way to describe a series of actions to perform on a selection of input data, the result being presented in memory or saved to disk. Say I want to explore how proposed changes to a robot footprint or safety zone affects the ability of a robot to revisit previous goals. In this case, I've just opened a bag using QGIS ROS that includes all previously requested goals. On the right side, I have a QGIS processing model that I put together. It effectively accepts robot poses, a robot footprint polygon or a radius, and an occupancy grid. By saving it to the project's toolbox, the pipeline is accessible by an auto-generated wizard. The result is a new layer consisting of all the goals that would not be reachable with a new footprint. From here, I could iterate on this experiment, I could publish results, and preserve the result data for future analysis. I also created a pipeline that finds all the occurrences of where a robot comes within its caution zone with the static map. These are contrived examples, but I want to convey the idea of being able to build easily modifiable workflows that let you explore a problem without yet having a strong sense of what the answer might be. It's very easy for us to modify these pipelines to involve other data sources or processing techniques. Or say I want to explore where congestion might occur due to loitering robots in my environment. In this case, all I did was open a bag, loaded it into QGIS, which takes seconds. And then, while this is only one robot, we could have easily added many robots from many bags, accumulating a large sample size on robot activity. And just through some symbology options, I elected to render this as a heat map. And so within seconds, I can get a much better sense of where my robot likes to loiter and where congestion might occur. I can use the same symbology on configuration of real-time data. Of course, the video is not going to work now that I'm up here. Oh, there it goes. There. So you do this in real-time data. And so while the video is sped up, I was watching this in real time as a robot navigated to a number of locations. It would be just as simple to subscribe to the position of many robots and watch them all in real time as well. What if I want to better understand the general Wi-Fi situation of environment? I think this is a pretty common problem. It's possible using Wi-Fi data, but that data doesn't intrinsically have a spatial component, so we'll just create one. I've subscribed to two topics here, the Wi-Fi connection and the robot's position. I've created a dynamic join between the two tables based on timestamp. This lends the robot's position measurement to the Wi-Fi connection measurement, and then I just drove the robot around for a few minutes. What's nice is that because these are subscriptions, these tables, the join, and the indexing are all updated in real time as messages are published. I then applied an interpolation algorithm to generate this surface describing Wi-Fi link quality. An interesting anecdote is that when I did this and showed my team, a colleague immediately responded, "That's not right. There's a Wi-Fi access point in that red area." Because this is being done in real-time data, I could iterate very quickly on gathering more data, verifying the results, and exploring our hypothesis that the robot was not changing access points properly. Within minutes, we were able to use these tools to verify that indeed there was a problem with Wi-Fi handoff. If we didn't take a moment to visualize these data, we may not have discovered that issue for a very long time. There's a lot of things I want to do moving forward with this project. I first want to improve the documentation, add some example applications along with sample data. I want to look at the possible use of existing rectification tools to make it easy to bind map frame to world frame. This would enable us to merge robot data with numerous other sources such as aerial photography or satellite imagery. I want to experiment with publishing data back into the ROS environment so you can do even more experimentation with data. I want to address some performance issues. Admittedly, there are some performance issues. When you get to a data set of over 1 million records, it starts to be slow. It takes a few seconds to render each frame. And I want to add ROS2 support because obviously we need to add ROS2 support. And of course, your collaboration on all these efforts would very much be welcome. Thank you very much.
Thanks for the presentation. Would this work for, say, robot manipulation, other kinds of visualization, I don't know, laser, camera, forces, torques, encoders?
Yeah, that's a really good question. Geographical information systems are really focused on the spatial relationships between things, usually in a very geographic space, traditionally, maps. My focus for this was on mobile robots. So your traditional case of we've got robots with wheels or some other motivator, and they move around an industrial or some sort of space, indoors or
outdoors. Say you want to track spatial relations between objects on a shelf. Could you do that?
That's a really interesting experiment. I don't want to say no to because I haven't seen it before done in GIS with kind of GIS tools. But if there's a spatial relationship there, then absolutely it's worth experimenting and trying. I don't exactly see why not.
Thank you very much, Andrew.
Thanks.